Hi there, this is Heath. We're looking at the second day of our material, which is on conditional statements and argument forms. Let's get started. For two statements, P and Q, the implication that P implies Q, or if P then Q, the implication is just another name for if P then Q, is the assertion that if P then Q. Whenever P is true, then the statement is evaluated for Q. So anytime P is true, we then move through the arrow and evaluate Q. And the value of Q is returned. So in this case, we return true, and in this case, we return false. Anytime P is false, Q is not evaluated, and the statement returns a default value of true. And so this is the truth table for P implies Q, which is on the next slide. P implies Q is true in all cases except when P is true, which does mean we follow the arrow, but then Q returns a false value. This table has three true values, and one false value. We've already seen another table that has three true values and one false value. It's this one here. It's the table for P or Q. Is there a way to rewrite P implies Q in terms of an or statement? So because the last column of the statement includes three trues and one false statement, this arrow statement, P implies Q, can be written as an equivalent statement using the or connector. What statement is equivalent to P implies Q? Well, we know the truth table for P implies Q now. It's this table right here. True in the first row, false in the second row, and true in the next row. And so if we want this to be P or Q in some order, this doesn't work. But what we want is this to return true every time that, unless P is true and Q is false. And so if we negate P, then any time that P is false, this returns true, and any time Q is true, this returns true, but this one case will return false. And so it is possible to write an implication, an if-then statement, using an OR gate, which, if you are coming from the point of view of designing digital circuitry instead of writing code, this is a fast digital circuit to implement. They're cheap, they're fast, they're nice to work with. But this has a further implication. If we can rewrite an if-then statement as an OR statement, then we can write the negation of an if-then statement as an AND statement because of De Morgan's law. De Morgan's law, remember from last time, is that if we want to negate an OR statement, that's the same thing as passing the negation in, distributing it to both P and Q, but changing the OR to an AND. And if we want to negate an AND statement, that's equivalent to passing the negation inside the parentheses to both P and Q, but changing the and to an or. And so, since we know that P implies Q is equivalent, we saw this on the last slide, to not P or Q, that means the negation of P implies Q is equivalent to the negation of not P or Q. And then by De Morgan's law, we can pass the negation inside the parentheses, and so the negation of P is P, and the negation of Q is not Q, and the or changes into an and. And so this is how to write the negation of an if-then statement as an and statement. I'm going to define some terms here. If we have an implication P implies Q, and we switch the order of the parameters, this is called the converse of the implication. So a converse is a different implication obtained by reversing the order of the parameters. For example, if we wanted to conform the converse of the statement, if x is positive, then 2x is positive, that would be the statement, if 2x is positive, then x is positive. This original statement, if x is positive, then 2x is positive, is a true statement. But it turns out that this statement is also true. If 2x is positive, then x is also positive. We have an example of a statement here in which both the original implication and its converse are true, but that is not always the case. These statements are not always logically equivalent. Here's an example of a if-then statement that is not equivalent to its converse. If x is positive, then x squared is positive. That's a true statement. But its converse says that if x squared is positive, then x is positive. And this can be false. For example, x could be -3, and x squared would be positive because x squared would be 9, but x would still be -3. And so these statements are not logically equivalent because it is possible for this statement to be true and this statement to be false. The contrapositive of an implication is the implication we generate if we switch the order of the parameters and we also negate the two parameters. So we start with P implies Q, but we end up with not Q implies not P. So for an example, if my original statement was, if it snows, classes are canceled. Well, the contrapositive of that is if classes are canceled, or sorry, if classes are not canceled, then it didn't snow. Are these statements logically equivalent to each other? And the answer in this case is yes, they are. And we can verify this by checking their truth tables. We know the truth table for P implies Q is true in the top row, false in the second row, and then true in all of the rows after that. But the truth table for the negation of Q implies the negation of P. Let's think about what's going on there. Anytime the negation of Q is true, that would say that Q itself is false. And so we're looking at these two rows here. If Q is false in either of these two rows, then the left side will be true, which means we do follow through the arrow and evaluate the right side. And the right side is what gets returned. Well, in this row, the right side would be the negation of P, and since P is true, the negation would be false. And in this row, since P is false, the negation would be true. And so we get these two values when we do follow through the arrow and evaluate the right side. On the other hand, any time that Q is true, this row and this row, the negation of Q will be false. And any time the left side of the implication is false, we do not follow through the arrow, we do not evaluate P, we simply return a default value of true. These two true values are default values because the right-hand side never got evaluated because the left-hand side was false. But it turns out that in every single case, this statement and this statement have the same truth value. 3 of the times they are both true, 1 of the times they're both false, but they're always the same, and so they are logically equivalent. All right. An argument form is a structural way of deriving new true statements from other true statements. We're looking at statements that have to be true in this case. This argument form is valid anytime whenever the statements are above the line or true, that they force the line below the statement below the line to be true. And if this is not a statement that must be true, then the argument form is invalid. And so another way of saying this is, if it is possible even if it's rare, even if it only happens once in a million, if it is possible at all for the statements above the line to be true, and a statement below the line to be false, then the argument is invalid. All it takes is a possibility of true statements generating a false statement, and that makes the argument invalid. I'll show you an example of a valid argument and an invalid argument. This is an example of a valid argument form. If we know that P is false, the negation of P is true, But we do know that one of these two statements is true. Well, we've already eliminated P. The answer then must be that Q is true. And here's how we can show that this is a valid argument form. Normally, there are 4 possible cases for the truth values of P and Q. Both can be true. P can be true and Q can be false. P can be false and Q can be true, or both statements can be false. But when we're testing for validity, we are looking at the cases where we already know that the statements above the line are true. Statements above the line are true. So I'll look at this statement first, and I'll try to color code this. Since the first statement is true, we know that P is false, and that rules out these 2 rows. These 2 rows do not apply if statement 1 is true. On the other hand, this statement is also true, and it says that one of these 2 statements, P or Q, is true. Well, this is not allowed. This does not apply. Since statement 2 is true. And by elimination, out of the original 4 possible statements we had, only one case, the 4 possible cases that we have, only one case remains. Knowing that these 2 rows are both true has eliminated the first row and the second row and the 4th row from consideration, and the only row that remains is a row in which Q is in fact true. And so Q is true by elimination. And so this argument form is valid. Here's an example of an invalid argument form. P or Q is true, P or R is true, and therefore we conclude that P is true because it's in both of these statements. Now this statement has 3 variables in it, so the truth table is going to be a little bit longer because we have to account for all of the combinations of P and Q and R. They can all be true. Or P can be true and the other 3 possible cases for Q and R play out. And then the same 4 cases with P being false can play out. These are the 8 possible scenarios that occur when we have 3 Boolean values. I'll color code these again. Since this first statement is true, then we know that at least one of P and Q has to be true, which means that this row can't happen and this row can't happen. And then since this statement is true, we know that at least one of P and R is true. Well, of the remaining cases, this can't happen. And so we started with 8 cases and we are down to 5 cases, but there is still a case in which P is false. And so even though P is true in 4 out of the 5 cases, it can be false. It's only false 1 out of 5 times, but it can be false. And therefore this argument is invalid. It's only valid if P is forced to be true, and it's not forced to be true. There is still some wiggle room there. So let's look at a couple of special argument types. This is a type called Modus Ponens. This comes from the Latin phrase for the way of affirming. It is an argument form that if we have the implication P implies Q, and we know the left side is true, then the right side must also be true. This is a way of putting Modus Ponens in words. If Louise gets promoted, then we will celebrate. Louise gets promoted, and therefore, as a conclusion, we conclude that we will celebrate. Is this a valid or invalid structure? It is a valid argument form. This is valid. And it's valid because we are starting with the knowledge that these two statements are true. And therefore, our possibilities are, if P is a statement, Louise gets promoted. And Q is a statement, we will celebrate. Then this is a statement, P implies Q. This is a statement P, this is the statement Q. And there are 4 possible cases for these 2 atomic statements to have their truth values. The top row, this first row, eliminates this from contention. Because in the second row, P implies Q is false. And we know that it's true. The second row says that P is true. Louise does get promoted. And in these 2 rows, Louise does not get promoted because P is false. And so these 2 rows are eliminated. And as a result, out of the original 4 cases, only 1 case remains. And in that 1 case, we can conclude for a fact that we will celebrate. This is true. And so this is a valid argument form. Modus Tollens. And there's a typo right here. This should say Tollens. And if you downloaded the handout for this section, there's a typo in the handout also. I apologize. This should be Tollens. This is a Latin phrase meaning the way of denying. And it says that if we start out with the knowledge that this implication is true, and the right side is false, in other words, the negation of Q is true, then the left side has to be also false. Here's an example of a modus tollens. If I eat too much, then my tummy will hurt. My tummy does not hurt. The right side is false, and therefore I conclude that I did not eat too much. This is also valid. It's valid because all of the cases in which I did eat too much turned out to be eliminated. I'm going to mess this up every time. Sorry. In the top row, if I eat too much, then my tummy will hurt. It says that this is eliminated. This is the case where P is true and Q is false. That makes the implication false. This row says my tummy does not hurt, so that Q is false. Well, in this row, Q is true, and in this row, Q is true. And so those are eliminated. We only have one row left, and it's the row in which P is also false. So the negation of P is true. And so this statement is it's not possible for not P to be false, because P is false in the only remaining case. And so this is a valid argument form. Is there a relationship between modus tollens and the contrapositive of an implication? Modus tollens says that if we have P implies Q and the negation of Q, then we conclude the negation of P. If we replace this statement with the contrapositive, then we get the negation of Q implies the negation of P. The negation of Q is true, and therefore the negation of P is true. But this is now saying that the left side is true, and therefore the right side is true. And this is now modus ponens. In other words, if we replace an if-then statement with its contrapositive, it converts modus tollens to modus ponens and vice versa. I want to show you briefly some other argument forms. Generalization is the argument form that says if I already know that an atom P is true, then I can connect that atom to any other atom, P or Q. And since I already know that the one on the left is true, I know that the or statement is also true. So I can use or to add more things, even if those things are false, because I've already pre-established that one of them is true. Specialization works the other way around. If I know in advance that this and statement is true, well, then I can conclude that this individual part of the and statement is true. I can also conclude that this part of the and statement is true. That is, if I have an and statement that I know is true, then I can simplify it and just look at each of the individual parts, and I know they have to be true. Elimination, if you have ever read Sherlock Holmes and you are familiar with the quote that says, whenever one has eliminated the impossible, whatever remains, however improbable, must be true, that's the argument form that he's describing here. If we know starting in advance that one of these statements is true, P or Q is true, but we can eliminate Q because the negation of Q is true and therefore Q must be false, then we can eliminate this one as being a possible true statement in this or statement. And therefore we conclude that even if P was very improbable to begin with, it must be true. Transitivity is the property that if P implies Q and Q implies R, then we can pass the arrows straight through and say P implies R. This one is true, and it is worth checking the truth table for this to see what happens. It turns out that out of the 8 possible cases for P, Q, and R, 3 of them are eliminated, and of the remaining 5 cases, 4 of them involve P being false, and so the R becomes irrelevant, and whenever the left side is false, then we return true by default. And the last form is cases. If I know that at least one of these 2 statements is true, well, it could be P, in which case P implies R, and therefore R is true. Or it could be Q, and therefore Q implies R, and so R is true. I don't know which of these 2 cases will be correct, but one of them will be correct, and therefore R will be true. A fallacy is another name for an invalid argument form, but it's usually applied we usually apply this term to invalid argument forms that are commonly seen. Arguments like ad hominem arguments, or straw man arguments, or asserting the consequence arguments. Any kind of argument, circular reasoning, that is so widely recognized as being a false argument type that it doesn't take a lot of effort to show why it's a fallacy. A clever original invalid argument that nobody has ever seen before, even though it's invalid, would probably not be called a fallacy. But technically the term just applies to any invalid argument. We just don't usually apply it that way. Here's an example. If Hayside, Virginia is a metropolis, so let's let that be statement B. Then it has tall buildings. So if Hayside is a metropolis, then it has tall buildings. However, Hayside is not a metropolis, and therefore it does not have tall buildings. This is not a valid argument. This is a fallacy. To some people, it seems like it's going to work because our understanding is that most towns that are not metropolises, do not have tall buildings. That these things tend to exist only in metropolises. But again, the rule is that if it's even possible for a small town to have a tall building, if it is possible for these statements to be true and this statement to be false, then this argument is not invalid. And it is definitely possible that Hayside could have a tall building. If I look at the truth table, the first statement is an implication, and that eliminates the second row. And the second statement says that P is false. Well, that means we can eliminate the case that P is true, because the negation of P is true, so P has to be false. And so we have both cases here where P is false. But we have not ruled out for a fact whether Q is true or false. We cannot definitely conclude that Q is false because it is still possible for Q to be true. Okay? And therefore this argument is not valid. Thanks for watching. We'll follow up again with the next section on Monday. Take care.